Hello, everyone. My name is Hibo. I'm from machine learning platform team at DoorDash. We also have our colleague Kunal here, who is actually the creator of Fabricator. So thanks to the other conference this week in Cupertino, I've got myself Apple Vision Pro to help steal Kunal's lines. Let's see how that goes. And thank you for staying to the end today for our talk. I'd like to start with a question. Why are we here for this talk? My answer I have in mind is that we all have directly or indirectly faced the struggle of improving scale and velocity for feature engineering. Thanks to all of the new model frameworks and vendor solutions that make models so much more powerful and at the same time easier to develop, the number of machine learning models and applications have grown tremendously. However, an estimated 75% of model development time actually goes into feature engineering. So our brain are hungry for food after a long day of conference. These new powerful models also have a hunger for large volume, good quality of data. This makes feature engineering velocity a vital offering on a good machine learning platform. Today, we want to talk about Fabricator, DoorDash's feature platform that helps us drive feature volume to 20x and improve iteration times from days to hours. In this talk, I'd like to begin with a brief overview of machine learning at DoorDash, followed by a context for where we started with feature platform. From there, I will summarize our major pain points and convert those into perception of an ideal feature platform design. We can then go through how Fabricator addresses that vision and deep dive into the components that make the vision a reality. Lastly, I'd like to summarize and share our results and learnings. Machine learning powers every aspect of DoorDash: restaurant recommendations, fraud detection, virtual assistants, and most importantly, how long it will take for my food to arrive. These are just some examples which all rely on the secret ingredient of ML that powers them. This picture comes from a well-known paper published by Google in 2015. The main takeaway is that the surrounding infrastructure to develop ML models and take them to production is vast and complex. For this reason, at DoorDash, we have a centralized machine learning platform to provide most of the surrounding infrastructure so that machine learning engineers and data scientists can just focus on the yellow box and make the models really good for our customers. The main goals for the machine learning platform are the following. We want to simplify and reduce the complexity in machine learning development process. To do this, we would provide the needed infrastructure, build it once, and have it leveraged by most machine learning teams within the company. Here's a pretty standard flowchart for our machine learning workflow. On the feature engineering side, the raw data is transformed into ML features, which are stored offline for model development and online into a feature store for predictions. On the training side, models developed by various teams are serialized into a model store. Finally, the prediction service loads models and features to handle prediction requests from clients. With the overview of machine learning at DoorDash, now I will walk over the journey of our feature platform. Feature engineering is quite central to machine learning engineering at DoorDash. When we started in 2021, we have about 400 unique features with 100 billion values. They're generated by 60 batch jobs and 11 real-time feature jobs. These jobs are created by a small team of 20 machine learning engineers. These features make their way into an online feature store, powering millions of predictions per second. At this time, our machine learning engineers and data scientists primarily focus on two areas. One, feature development, which focus on the creation lifecycle of a feature, resulting in periodic persistence of features into an offline warehouse. and 2, feature serving, which focus on low latency serving of these features in production. As a ML platform, our primary offering was a scalable and efficient serving store for features. The broader data infrastructure also had a scalable solution for ETLs that write those into a data warehouse. However, everything else was a manual process. Data scientists had to individually author each ETL job that produced their features, write their own scripts to consume them for model training, and repeat that feedback loop until they were satisfied with the feature. And then they interfaced with the machine learning platform, putting these features up for serving through a different service layer. As you can see, there are quite a few bottlenecks in this process. First, there's too much fragmentation. Data scientists have to interface with multiple loosely coupled systems: data orchestration, data warehouse, feature source, notebook, etc. Each system comes with its own learning curve and an additional manual setup as well. It is hard to maintain the semantic meaning of a feature along this life cycle. And 2, feature evolution is slow. Different systems tend to evolve differently, and best practice change based on the framework you use. Every change requires all the connected systems to be compatible with the flow, and who owns that charter? It is also an unreasonable ask for data scientists to tune their operations based on what's best for the infrastructure choices. For example, should they use Snowflake or Delta Lake Warehouse? Should they use Spark or SQL-based transformations? How these decisions affect feature life cycles. Third, there's no control plane. We reach the point where there are enough machine learning and data science teams to be unable to keep track of the features the other teams build. How do you share best practice for engineering features across communities? How do you learn which feature exists at all? And more importantly, how do you keep track of your features on a daily basis and then maintain operational awareness? Where should we go from there? There are one of 2 choices: incremental improvements or a fresh start. We then try to imagine what the latter would look like. We spend a while connecting with our community and multiple industry solutions, as well as to understand how to address the gaps. An ideal feature platform should have the following. First, a single entry point. Users should be able to set up the entire feature lifecycle, from dev to production, within a single interface. Second, semantic feature representation. The platform should natively understand what a feature is, how it is stored, what are its constituents, and how should it be served. Third, simplified abstractions. As far as possible, the end user shouldn't have to deal with low-level details. What is the storage format of the features? How to optimize compute and I/O for my code? How to monitor my daily runs? The feature platform should abstract this away from users and have them focus on feature development itself instead of the infrastructure. Fourth, high iteration velocity. We should make adhere to code as crisp as possible. Feature changes quickly. A DoorDash order takes minutes to deliver, and it shouldn't take a week to deploy feature changes. Finally, automatic feature lifecycle management. Things like upload to feature store, monitoring, orchestration, and everything else should be automated by the platform. So putting a picture to all the words, we expand the scope of platform to 3 areas: feature registry, feature development, and feature serving. We also introduced a new area around feature management. Additionally, we focus on all interactions going through a single entry point of the feature registry. This build-up brings us to our main topic for the talk today, Fabricator. Our vision is to enable data scientists to declaratively define efficient end-to-end feature pipelines and automate the operational lifecycle of features. We focus on delivering our vision for ideal feature platform through three core ideas. First, we need a feature registry that allows users to define their entire feature ecosystem in a simple, tunable way. It should be globally visible to the rest of our infrastructure. We also focus on minimal code approaches rather than no code approaches. Two, we need a layer to execute the declared definitions that bridges the infrastructure through simple APIs, focusing on the goal of high velocity. The platform should also provide a way for them to playground features quickly and experiment in an execution environment that was identical to the production setup. An environment that would let users focus on their business logic rather than the low-level framework details. Third, once they can describe their feature lifecycle and generate them effectively, all the remaining plumbing should be free. Orchestration, monitoring, serving, optimized storage, everything should be automatic. Let me restructure our ideal platform in terms of the components we just highlighted. The registry still forms the central entry point. The unified execution environment focuses on solving the generation lifecycle of a feature, either in a playground or production modes. And then infrastructure automation solves the rest of our downstream goals around serving and management of features. With that, let's take a deeper look at the three pillars. For this dive, I'd like to highlight the architecture from the lens of a production use case. For our search ML team, one interesting feature is a consumer's engagement history over varying periods of aggregation. We will take a look at the whole life cycle of these features as we go through the components. There are a few salient points that highlight the architecture of the feature registry. The registry allows users to define their entire feature semantics in YAML. This makes the registry DSL approachable and highly extensible. However, each of the YAML objects in the registry are backed by a protobuf definition. This allows us to be flexible with structure, testability, and backwards compatibility. Each of the objects are also persisted in a backend database and are gated behind a microservice that allows global access to these definitions for the rest of our service mesh. Lastly, the YAMLs are enacted through GitHub and are continuously deployed on every change, making the go live step for any change just a few minutes, just like a DoorDash order. So how would a search MLE begin their journey with the registry? It starts with the YAML source definition, which focuses on the generative lifecycle for a collection of features into offline storage. The schema allows variable methods of generation, with the other pieces staying the same. We also support real-time transformations with the computational logic. In reality, features are different from generic datasets in the semantics of their columns and how they behave. The source specification can also encompass a general dataset definition that are intermediates for downstream features, or even datasets that are precursors for training or validation workflows. To highlight some benefits of this design. First, feature definition evolution is super easy. We could confidently extend the definition schema without worrying about breaking existing features. Second, it makes the underlying infrastructure flexible. We could adopt new storage and compute paradigms without significant shifts. Third, the definition could be easily consumed by users and multiple downstream services for integration. Definition is only part of the puzzle. A bigger challenge is getting features executed. How does a SQL result get stored into a Delta table? Or better yet, how do we pipe real-time Flink transformations into the feature store? The answer lies in our execution environment. We build and maintain a library suite that provides the translation layer of the YAML configurations. The suites focus on instantiating these definitions natively in Python with the utilities to actually execute them as jobs. Apart from providing easier onboarding and higher velocity to feature development, this environment also focuses on providing simple black box optimizations for common feature engineering roadblocks. Let's dig a little deeper into contextual executions. Within Fabricator, contexts represent Pythonic wrappers over the YAML definition. This enables the libraries to execute feature jobs efficiently. We saw earlier how we can define generated YAMLs for sources, and list one or more features derived from that source. We provide a feature context wrapper that encapsulates those objects within a single execution context. This is information complete on how a user job should be run. Next, we also provide a generic Spark job that knows how to execute any provided feature context. All of this definition reduce user code to a really small, clean piece of efficient code, given their YAML definitions. They simply initialize a context from the named object in the registry, pass it to the upload job, and run. And voila, the features will be produced and written out to the intended data source. Again, to highlight the benefits here. First, most jobs are no code. Each of the library constructs we showed are extensible and available to the users to extend or customize only if their business logic requires it. However, if not, their jobs are entirely codeless. A simple SQL transformation can run entirely from the SQLs provided without any code checked in. Two, high fidelity testing. Notebook clusters are identical to job clusters, so you can run the exact same code in your test environment and expect data to get written to sandbox data stores instead. In the notebook environment, the context point to staging versions of all of our infrastructure. Three, efficient execution. We package best practice of tuning connectors, resources, and other low-level details like data partition into the library as well, leaving the user free from those concerns. The final aspect of design I'd like to cover is infrastructure automation. With central registry and unified library, everything else comes free. This is the part we like the most, as it's free to our users. We'll talk about the cost later. The key parts here are job orchestration, feature online serving, and feature discovery. The job definition enables a few key automations for orchestration. From the trigger spec, a DAG of all dependent jobs are automatically constructed. Each job by default is partitioned by date. This allows users to backfill large scale of historical data in parallel. User could optionally backfill months of an entire DAG of jobs through a few clicks. Next, the sync section in the source definitions allow automatic materialization of features. Based on the configs, features are uploaded to our scalable feature store, ready for serving at model prediction time. Again, we can see a few lines of YAML here in the source definition enables the feature to be uploaded from offline to online feature store. Finally, the centralized source definition and Spark execution allow us to easily integrate with data catalogs like Amundsen, AWS Glue, and of course, Unity Catalog. Just like food, teams and people have different appetite for how to view and consume the data. With integration to our analytics engine service, data generated by Fabricator can be easily queried with Databricks Notebook, Apache Trino, and Sigma dashboards. Okay, in the last section, we'd like to share our results and learnings. First, let's flash back to this slide for 2021 and take a note on these numbers. Now, we can see that Fabricator has helped us grow by 20x in almost all metrics. On the learning side, Fabricator is a good example of how building products instead of systems help drive adoption. With Fabricator as a single entry point, instead of multiple systems, we're able to grow our feature platform by 20x easily. After the initial development and onboarding, all the rest of the options are self-served, with minimal support needed from the platform team. Secondly, building a paved path for most common patterns while leaving room for customization proved to be another major driver for adoption and velocity. And finally, building the product with a demand for extensions and integrations takes a long way. When we started with Fabricator, we tried to design and implement functionalities with clear boundaries. Then we tried to leverage services built by our partner teams to handle different functionalities. A good example is our Spark job management. We started with using Databricks REST APIs directly. As our data control team built a Spark job execution manager service to manage Spark job life cycles and optimize for compute cost, we dedicated the Spark compute to that service. With the scale of our jobs, we're seeing very good cost efficiency improvements from this integration. Great adoption is not without risks. The quick growth comes with scalability, reliability, and efficiency problems. For example, the declarative feature pipelines made it very easy to create feature jobs, and it's great for adoption. However, we also noticed these problems. We started with a platform SQL warehouse, and it cost skyrocketed with the increasing adoption. Jobs also become slow at points with resource contention. The complexity and data volume of the Spark jobs also significantly grew over time. Some of these jobs had long runtime and high costs. Lastly, as it is easy to quit jobs, it's also easy to forget about them. With the growing number of feature jobs, we started to notice that some jobs were not needed and abandoned. We had to come up with some simple solutions for these problems. For the warehouse and compute problems, we introduced team concept for resource isolation. Each team brings their own warehouse, and the jobs are also queued based on the team. For Spark performance and cost, we worked with our Databricks solution architect team to come up with guidelines for performance tuning specific to our use cases. As mentioned previously, we also leveraged our Spark job execution manager service built by the data control team for automatic optimizations to reduce job cost without affecting jobs' latency SLAs. Lastly, with the team ownership on jobs, we attribute and report job cost based on teams for user-driven cost reduction incentives. And finally, for abandoned jobs, we have built system jobs to detect and auto-disable continuously failing jobs. We are also looking to leverage the data lineage to active models as well as feature importance to identify unnecessary or low returning investment jobs. Functionalities like automatically backfilling downstream jobs to create historical data for model training are great for dev velocity. Who wouldn't want this functionality by default, we thought. However, this turned out to be extremely expensive to do for large and deeply nested decks. It's actually better to only backfill downstreams upon an explicit flag. Let's revisit the three core components of Fabricator, which are the feature registry as a single entry point, the unified execution environment achieved by a library suite to abstract away common job execution logic, and finally, the infrastructure automation for orchestration and integrations. This provides a single entry point, as well as an end-to-end experience that is great to our users. However, this also makes the system itself very complex. Many times when a job fails, and the job do fail due to various reasons, it's very hard to tell systematic errors apart from individual user or data error. To solve this problem, we have implemented functionalities to categorize errors as much as possible. We also realize that traditional system observability tools are not enough for those mostly heterogeneous jobs that still share common components. We have to also export our job metrics to Delta tables and join them with data from Databricks system tables to do analytical queries for error detection and cost optimizations. All right, that brings up to the end of this talk. Thank you very much again for staying to the end and walking over the journey of Fabricator with me. Now it's time for QA.